continue on our discussion of walking with rational functions. And what I want to build towards right now is thinking about how graphs of rational functions will work. So here's one. Let's try to graph this, x plus 1 over x minus 1. And I'll develop two strategies for graphing something just like this. The strategy I'll try right now is, it turns out the graph of this thing is just going to be a shift of 1 over x, which just shouldn't be obvious right now. But it will be obvious soon if we do some polynomial long division. It won't even be very long division because there's not very much going on here. So let's try to do that. Let's take x minus 1 and divide it into x plus 1. And I've pre-drawn it like this so that I could be sure not to screw up which one goes where. Right, like the thing on the top goes inside of the box, right? Yeah, okay, good. So now I'll follow the algorithm. What should I multiply x by to get x? 1. So, x plus 1 over x minus 1 is 1 plus. So now I take this 1, multiply it by x minus 1, and subtract the result. So minus x minus minus 1 plus 1, 2. So what's the remainder? 2. Right, so this is degree 0, that's less than degree 1. So this has a remainder of 2 over x minus 1. So x plus 1 over x minus 1 is the same as 1 plus 2 over x minus 1. Here's why that is useful. I'm going to rewrite that in a way that will maybe seem more complicated, but I think it'll make it more obvious how to graph the thing. This is the same as 2 multiplied by 1 over x minus 1 plus 1. Do you agree that that's the same? Here's why that's useful. That's something that we know how to graph by transformations. That looks like you would start with just 1 over x. Then you deal with this 2. What would that 2 do to the graph? Yeah, say that. Someone respond, I think. It'll like double all the y values. It'll stretch the thing vertically. Was it you? You said the right thing, I think. Okay. Then there's a plus 1. What will that do to the graph? Up 1 and right. Cool. So we know exactly how this graph should look. It should be start with y equals 1 over x. We know how that looks. We will double the y values. And that looks like the y values have been about doubled. Next we will go left. Nope, you said right 1. And up 1. So maybe the best way to think about that is it looks like there's this vertical asymptote of x equals 0. What will happen to that vertical asymptote when I take it and shift it right 1 and up 1? I couldn't quit here. Yeah, it'll just become x equals 1. So you'll shift it right 1, you'll get x equals 1, then it'll go up 1, but it's already a vertical line. So you'll have this vertical asymptote at x equals 1. You have this horizontal asymptote at y equals 0 beforehand. What happens to that when you do this transformation? Goes to y equals 1. And then it'll continue to look roughly the same. And I think the problem says that we want to have the right, no, it doesn't say anything about having the right intercepts. I'm going to be picky and try to have the right intercepts. But whenever you do these graphs by transformations, maybe the intercepts don't come along for free all the time. How would you find the y-intercept of this thing? Plug in 0 for x. What do you get when you plug in 0 for x? I think you get -1. Whenever you see a negative in the denominator, it's really the whole thing that's negative. So, let's make sure I have the right y-intercept. How do you find the x-intercept? Set y equal to 0, solve for x. Before or after we do the division, where does it look easier to set it equal to 0 and solve for x? I think before. In fact, we have a trick. We just set the numerator equal to 0. If we want x-intercepts, easy to set the numerator to 0. What do you get? I hear a -1. Nice. Cool. So that graph has gotten ugly, which is why I gave myself space here. So an intercept, horizontal asymptote at y equal to 1, vertical asymptote at x equal to 1. It has to go through this y-intercept, then the x-intercept. 0, -1, -1, 0. Cool. That feel pretty okay? Nice. So, maybe there's one thing you notice here. You managed to track these intercepts by just seeing how they moved under the transformations. And whenever you see like linear function over linear function, you can totally do that. As rational functions get more complicated looking, we'll want to be a little bit more sophisticated about horizontal asymptotes anyway. So the next result is going to give us a way to easily find horizontal asymptotes without really doing any work. And the logic isn't going to be that terribly deep. In order to think about this, so here's what the following theorem says. If you have a rational function p of x over q of x, if the degree of q, the denominator, is bigger than the degree of p, the numerator, then there's a horizontal asymptote at, and then we'll just say where it is. And in order to get that, let's think about what horizontal asymptotes mean. The horizontal asymptote is what happens when like you plug in a really, really big value for x. If there's a horizontal asymptote, the y value should get close to some line. So give me, I think we're going to do an example, and then we'll figure out what's going to go there. Give me a polynomial. Any polynomial. Maybe something not too complicated because it needs to fit in the margin right there. X plus 2. Give me another polynomial that has degree bigger than that polynomial.
X squared plus 2.
Excellent. Creative choices. I like it. So, in order to think about the y-intercept, nope, the horizontal asymptote, let's see what happens when we plug in x equal to a really big number. 10,000 seems big enough. Let's think about what this is pretty close to. So let's call this y. If you take 10,000 and add 2 to it, does that really change the value of that number by much? So the numerator is basically just 10,000. In the denominator, let's see, 10,000 squared will be for like 8 zeros. So maybe I'll use scientific notation. 10 to the 8th. So an 8-digit number, when I add 2 to an 8-digit number, does that really change the value of it by much? Oh, so I can basically ignore that. So what I see here is a 4-digit number divided by an 8-digit number. What is that going to be about? That's not quite. So that would be like 10 times 10 times 10 times 10 divided by 8 tens in a row. I've run out of space, but there are 8 tens in the denominator. So what cancels? 4 of those tens. Oh, neat. And if I took that 10,000 and just made it bigger, that whole result would just get smaller. So the y values are getting really close to 0. Because the denominator is just way bigger than the numerator. The horizontal asymptote is at 0. And maybe we'll even see that visually. Let's graph exactly that. X plus 2, and then we'll divide by x squared plus 2. There's the graph. And I want to see what happens for really big x values. So let's see what happens from x equals 100 to x equals 10,000. There we go. And the y values are now ranging from negative 0.01 to 0.01. Those y values look like they're getting real close to 0. And I've already zoomed in an awful lot in the y direction. So yeah, this has a horizontal asymptote at y equal to 0. And the reason it has it is just because you're dividing by something that's way bigger than the thing that you have on top. I guess that makes sense. If you divide a number by a number way bigger than it, you basically get 0. Cool. The next case, if the numerator, if the degree of the denominator is equal to the degree of the numerator, then let's try to find the horizontal asymptote again. Give me 2 polynomials of the same degree. I guess maybe I can write this one down. X to the 5th plus 4x squared plus 3. Let's put a 2 there. 3x to the 5th minus 25. And we can play the same game. Let's imagine plugging in like a 20-digit number. If you take a 20-digit number and raise that to the 5th, you get a 100-digit number. Take a 100-digit long number and subtract 25. Does that 25 matter? If you multiply a 100-digit number by 3, does that matter though? Yeah, you triple it. That's significant. So the denominator here is basically just 3x squared, 3x to the 5th. And now let's look in the numerator. So again, take a 20-digit number. Then 2x to the 5th is a 100-digit long. Take a 100-digit number, add a 40-digit number. Does the 40-digit number actually matter in comparison? Not really. You take something that's 100 digits long, and that's like 10 to the 60th times as big as this. That's like a huge difference. That's basically ignorable. Does the plus 3 make any difference? So when you plug in a really big number, if you want to be approximate like this, you can just throw away everything but the biggest terms. 2x to the 5th. All right, so now I see 2 times this 100-digit number divided by 3 times this same 100-digit number. Anything cancel? Yeah, say it loud. the x to the fifths. So it just became 2 over 3, and importantly, it was this 2 over 3. Whenever you take degree of denominator equal to the degree of the numerator, there is a horizontal asymptote, and that horizontal asymptote is at the leading coefficient of the numerator divided by the lead coefficient of the denominator. And I don't know, let's see if we see that happening in a graph. So let's graph exactly that same example polynomial. 2x to the fifth plus 4x squared plus 3 divided by 3x to the fifth minus 25. And that should allegedly be getting close to y equals 2 over 3. Going to make that dotted so it's clear it's a horizontal asymptote. Even at this scale, does it look like the line graph is getting real close to that blue line? So whenever the numerator and denominator are the same degree, you want the horizontal asymptote. Just forget about everything but the biggest term. And you know what? Let's play the same degree. See what happens when p is bigger than the degree of q. So maybe I'll take this example. I'll take the denominator and lower its degree a little bit. And we'll just see what happens. Let's just make that 5 into a 4. That looks like it has a horizontal asymptote. It looks like it has an asymptote. It looks like it's that non-horizontal line. So this thing has an asymptote. I'd call it a slant asymptote or an oblique asymptote instead. It doesn't have a horizontal asymptote. Let's lower it again. Does that look like it has a horizontal asymptote? In fact, it looks like if you zoom out far enough, I think I'm going to see that vertical asymptote still. And then I'll see what looks like a parabola. Oh, neat. Do you think it, like, why a parabola? What about this do you think caused that parabola? What's the degree of the numerator? Degree of denominator? 3. Oh, the difference is 2. Asymptotically, I think this should look like something like x squared. So, whenever p is bigger than the degree of q, there is no horizontal asymptote. Maybe I'll put this in parentheses. There might be a slant asymptote. Oh, God damn it, Chris. There might be a slant asymptote under those circumstances. And how many people have already looked at the homework that involves the word slant asymptote? Oh, okay. It is in Canvas. I don't remember. At this point, I think I need to rejigger like the homework assignment dates because I think it was posted for yesterday, but we're only now mentioning it. For details about slant asymptotes, I point you to a place in the book where you can read about how to use polynomial long division to find it. Groovy. Feel all right now? Let's just use this fact to make some predictions. Where are the horizontal asymptotes of that first rational function, if indeed there are any? So to answer that question, let's ask this first. What's the degree of the polynomial that is the numerator? What's the biggest power you see on the x on the top of that fraction? What's the same thing but in the denominator? 4. So now let's figure out which bullet point we should apply. Is the denominator bigger degree than q? No, so we don't apply this one. Is the degree of the denominator equal to the degree of the numerator? Of Cool, so we applied this rule. The horizontal asymptote will be the lead coefficient of P divided by the lead coefficient of Q. What's the lead coefficient of P? 1. Because there's like a 1 right here. What's the leading coefficient of Q? So the leading coefficient will be at, the horizontal asymptote will be at y equals 1 over negative 2. Does that simplify? Yeah, I guess the negative shouldn't be in the denominator as all. It's negative 1/2 or negative 0.5. Cool. Think you could apply that same technique to the remaining 3? Cool, do it. I'll give you like a moment for that. Cool. We feel good? Where's the horizontal asymptote of bottom left? And here our call for 0. Nice. Degree of the top is 4, degree of the bottom is 5. Numerator loses, so there's a horizontal asymptote at 0. Notice, alternately, instead of remembering any of those rules, we could just remember, well, just look at the leading columns. The denominator wins, so it's 0. This one, where is this horizontal asymptote? Here on 1? There is none. In fact, the top is degree 5, the bottom is degree 3. That'll look like a parabola when using that. Its asymptotics will be roughly parabolic. All right. So, what I think I want to close with is an example of putting all of the things we've developed together into sketching a graph by hand, which we can then check using a machine. Let's sketch a graph of that. X plus 1, x minus 2, all over x plus 2, x minus 1. So, let's make sure that our graph has the right intercepts. So I guess that means we have to find them. It has the right vertical asymptotes, so we got to find them. Has the right horizontal asymptote, and is positive and negative in the right places. And that bottom bullet point is where we'll spend most of the FR. So, let's go through it. Where are the x-intercepts first? How do you find the x-intercepts of a rational function? Set the whole thing equal to 0. Alternately, you can just set the numerator equal to 0, because you can't divide by something to turn something equal to 0. X plus 1, x minus 2 equals 0 to get x-intercepts. Oh, neat. Is that super easy to set equal to 0? Yeah, what are the solutions? Negative 1 and 2. So negative 1, 0 is one of the x-intercepts. 2, 0 is the other. Let's indicate those. Negative 1, 0. 2, 0. Vertical asymptotes next. How do you find the vertical asymptotes of a rational function? Oh, wait, y-intercepts too. How do you find the y-intercept? Plug in x equal to 0 and see what happens. To get the y-intercept, set x equal to 0. 0 plus 1 times 0 minus 2 over 0 plus 2, 0 minus 1. If you're very careful while evaluating that bit of arithmetic, what do you get? I plot a negative 1. I hear a positive 1. there anything others? All right, well, let's maybe even just do math by democracy. -1. +1. All right, let's check. I think the positive ones have it. 0 plus 1 is 1, multiplied by 0 minus 2 is -2. So that's negative. Divided by 0 plus 2 is 2, times 0 minus 1 is -1. -2 over -1. The negatives cancel. -2 over -2. The negatives cancel. So I think the positive ones had it. So, yeah, be careful with negative signs. 0, 1. And one of the neat things about this stuff where you graph by hand is if you would wound up continuing to run with that 0 and -1, you probably would have painted yourself into a corner while trying to sketch the graph and seen something really silly happening. And then you'd know to go back and check what you did. All right, particle asymptotes. How do you find those? / just where are the particle asymptotes? So the particle asymptotes happen when you divide by 0. So how do you check for that? Yeah, say it louder. Set the bottom equal to 0. To find the particle asymptotes, set the bottom equal to 0, x plus 2, x minus 1 equals 0. Oh, is that like easy to set equal to 0? Yeah, so I've made like the algebra steps here easy by giving you something that's already factored. If it won't factored already, maybe you'd have to use the quadratic formula or factor it. So the particle asymptotes are x equals -2 and x equals 1. X equals -2, x equals 1. Horizontal asymptotes. Let's check. What's the degree of the numerator? What's the degree of the denominator? 2. Cool. So whenever the degrees are tied, we need to take the ratio of the leading coefficients. And I guess that would mean that we'd want to, like, imagine foiling out the numerator and denominator, seeing what the leading coefficients would be. If you foil out the thing on top, then what do you see in front of the x squared if you did that? A 1. If you foiled out the bottom, also a 1. So where's the horizontal asymptote? 1. Oh, and notice, that means that, like, all the stuff that I just said is probably stuff you could do in your head without writing a whole bunch of stuff. So, you know, that's nice. Horizontal asymptote at y equals 1. Notice one thing we see. This graph is definitely going to hit its horizontal asymptote because its y-intercept is at the same y value as the horizontal asymptote. So, that is definitely going to happen in this example. So the next thing we're going to do is try to graph this thing so that it's positive and negative at the right times. And the only places where it could change will be vertical asymptote, because it could jump from plus infinity to minus infinity like 1 over x does. At an x-intercept, it could crash through the x-axis there. At a vertical asymptote, and at an x-intercept. So I'm going to play this game where we like check some sample points to decide where it's positive or negative. That seem like a plan? Give me an x value you could check to the left of -2. Here are -3. And we'll do that and we'll get like some computational result. And then I'm also going to try to encourage an alternative strategy to what we're about to do. So let's do it. Let's plug in -3. We'll get -3 plus 1, -3 minus 2, negative 3 plus 2, negative 3 minus 1. And all I care about is this positive or negative? And we can do that by computing the thing. Alternately, just type positive or negative. I hear a positive. Did you do that by actually computing it? All right, that's fair enough. What positive number did you get? 10 over 4. Okay. Here's the other strategy. Negative 3 minus 1, is that positive or negative? Negative, this next piece? Negative. Negative times a negative is positive, so the numerator is positive. Negative 3 minus 2, positive or negative? Negative times a negative is positive, so denominator is positive. So the whole thing's positive. So that means that for all x values to the left of negative 2, it has to be positive, and then it needs to get from asymptote to asymptote. Does that feel pretty okay? I just thought that we didn't even have to do that computation because we know where the horizontal asymptote is. And that's basically like already knowing a computation. If you plugged in x equals negative 10 trillion, about what y value would you have to get? 1, because we know the horizontal asymptote. Oh, 1 is positive. So for a really, really extreme negative x value, you know the result's going to be close to negative 1. So you could have skipped this computation entirely just because you knew the vertical asymptote. Similarly, if you plugged in a really extreme and positive x value, what will the y value be close to? Also close to 1? Oh, that's positive. So I need to go from that horizontal asymptote down to that intercept. Now I actually have to check some sample points. Next, check the sample point between negative 1 and 0. And I just care if it's positive or negative. Give me a sample point between negative 1 and 0. Nope, between negative 1 and negative 2. Negative 1.5. Good choice. There is no need to be fancy there. Negative 1.5 plus 1. And all I care is this positive or negative? Negative 1.5 minus 2. Divide by negative 1.5 plus 2. Negative 1.5 minus 1. Just this piece. Negative 1.5 plus 1. Positive or negative? Negative, because negative 1.5 wins. Negative 1.5 minus 2. Negative. So the whole numerator will be positive. Negative 1.5 plus 2. Positive, because the 2 wins. Negative 1.5 minus 1. Negative. So the whole denominator is negative. So the whole thing is negative? Oh, neat. That means it goes from this x-intercept, it has to become negative, and get to the vertical asymptote. That feel good? All right, the next region is between negative 1 and positive 1. Have we already checked a sample point in that range? Yeah, we know the y-intercept, right? You get the y-intercept by plugging in a sample point, a very specific one. So you know this thing's going to be positive. And maybe we'll just see how people are recognizing a pattern now. Between 1 and 2, do you think it'll be positive or negative? I hear a negative. Should we check a sample point anyway? Let's do it. What's a sample point between 1 and 2? Excellent. 1.5 plus 1. 1.5 minus 2. 1.5 plus 2. 1.5 minus 1. And let's just check each one. 1.5 plus 1. Positive times negative all over positive times positive. So the whole thing will be negative. Cool. So there's what the graph of this degree 2 divided by degree 2 rational function looks like. And maybe just one thing worth pointing out, we definitely had to cross that horizontal asymptote to accomplish this. So you just don't worry about crossing the horizontal asymptote, it can happen. I don't know, maybe another, let's see what else we can just read off. Is it even or odd? No. It looks like for each y value we see 2 different x values. So if you were asked to solve this thing is equal to some y value, it looks like you usually get 2 different solutions. I guess that makes sense because it's quadratic. Cool. So with 5 minutes-ish left, I think it's worth starting in on the next section. Let's do that. So let's talk about quadratic inequalities. And we already have a strategy that solves inequalities, right? I think the point I want to get across is the strategy we have won't work. There's something that will go wrong. And we'll see what goes wrong, and starting on Monday, we'll in detail see how to fix it. So, let's try to solve x plus 1 over x minus 1 strictly bigger than 2. And we have a strategy. Whenever you want to solve an inequality, step 1, figure out where equality happens because that's where inequalities can change. This is where the graph could go through the x-intercept. Go through this y value. So, let's solve equality. X plus 1 over x minus 1 equals 2. Does that look like something we know how to solve? What's a good first step? Multiply by x minus 1. Right, there's not just a single x, so you can't just undo everything in sight. But the most annoying thing on the left-hand side is that there's division. So make it so there's not division anymore. Clear that denominator. X plus 1 equals double x minus 2. And maybe even do some distribution. 2x minus 4. So x plus 1 equals 2x minus 4. Does that look easier to solve? Yeah. Because I doubled it twice. I appreciate that. All right. Does that look easier to solve than the thing we started with? And now actually looks correct? All right. I guess get all the x's onto the same side, get all the non-x's onto the other. Bigger x's on this side, so let's move the x's to the right. Subtract x to the other side to get x equals, add 2 to the other side, x equals 3. Neat. So it looks like there's this point at x equals 3. And the game we would now play is check some sample points to the left and to the right and see what happens. Give me an x value that is bigger than 3. 4. Let's check x equals 4. We'll get 4 plus 1 over 4 minus 1. Let's see, that's 5 over 3. I want to know, is that bigger than 2? Is it bigger than 2? No. And I guess one way to check, if you have some complicated inequality involving a fraction, is this is the same thing as multiplying both sides by 3 and asking is 5 bigger than 6? Is 5 bigger than 6? Now definitely not. So that means all of these points should be excluded. Now give me a number to the left of 3 that we could check. Let's try 2. Oh, maybe I'll encourage someone who wants to do something independent to also check what happens at x equal negative 10. But I'll plug in negative 2. Nope, x equals 2. So next let's check x equals 2. We'll get 2 plus 1 over 2 minus 1. That's 3 over 1. Is that bigger than 2? So it sure looks like by this, all of these should be included. So it looks like the solution that I'm seeing, I wanted to solve strict inequality, not loose inequality, is negative infinity to 3. Now, before I let you go, I need to convince you that this is wrong. To convince you that this is wrong, I'm going to pull up a computer-generated graph, and we will look at that to see what the solution looks like, or to see why this solution looks wrong. So let's graph x plus 1 divided by x minus 1. And let's compare that to, oh, Jesus Christ, Chris. There. Compare that to y equals 2. In fact, we can just do this. Y bigger than 2. So the green region represents everything with y bigger than 2. Does it look like for x's, all of these x's, the red curve is in the green region? No, so this is just wrong. Does it look like something interesting happens at that vertical asymptote? It looks like the inequality starts being true at the vertical asymptote. And then it continues on to this place where we knew it would change. So the graph says that this is just wrong. In order to fix this, well, we'll just add an extra step. In addition to finding solutions to equality, we will have to find vertical asymptotes. If we do both of those things, then we'll be able to solve rational inequalities. We will fix this on Monday, I suppose. Yeah, absolutely. Wherever you find yourself in that situation, yeah, you can ask at the beginning. Yeah. Yeah, it's also available as a PDF online. You know how to get to the course webpage? Yes. Yeah, it's there. Oh, yeah. They're for sure. Yeah, that's reasonable. They both move. Okay, so by my records, so you want like how far back do you want to go?
I got good vision.
Okay. That corner is open. In fact, is that right? The whole back row, the right half back row is open. There are a few people who sit on that side, but there's some open seats back there. Oh, yeah, but I mean, I have a copy too. Yeah, that's funny. I don't repeat the thing I said earlier. Ask me at the beginning if you don't have it. Yeah, that's copying it in. Oh, that's absolutely reasonable.
I didn't mean to do that.
Yeah, so yeah, then don't use these in class. Yeah.
You're out. I wasn't sure because I looked at the syllabus and it just like had the 1, 2 o'clock time, but I wasn't sure if that was the start of it.
Oh yeah, that should be the start time.
Okay.
Today's Friday? Yeah, 2 p.m. to 3 p.m.
Okay, perfect, thank you.
Yeah. Oh, I should fix that. I guess it doesn't haunt anything